boson.
I just switched it. Oh.
Yeah.
How about now?
Yeah.
Okay. So I also thank the organizers to invite me for my first trip to Brazil. I will have to talk about slightly different things from what we have heard during the workshop, because I'm more of a user of the results that were presented during the week, even though there will also be some results on alpha S, for example, from the Electroweak fit. But basically, I want to tell you how these fundamental parameters, and mostly fundamental QCD parameters, interact with results from the Electroweak kind of fits. So these are global fits in the sense that any information that is relevant for for standard model physics, let's say, but mostly Electroweak physics, will have to be considered. There are the by now old results from Z-pole experiments. They are old and they are published in final papers, and yet they keep shifting around because some of the inputs that had to be used to extract some of the observables keep changing, and I will present some very recent examples of that. Then we have low energy precision experiments. I hope I have time to at least give you a flavor what's going on in that direction. There are the heavyweights. We have already heard a lot about the top quark mass, and it is of utmost importance in the global fits if we then discuss it in the context of the Higgs mass and the W mass and so on. And then it's also necessary to have inputs like the charm mass, the bottom mass, delta alpha, and so on. The masses have been discussed here, delta alpha not, but they also enter in a correlated way. There are different groups and different programs that do these kinds of fits. I'm using my own program, GAP, that also enters the Electroweak section of the PDG. Then there is the G-fitter group that has a different scheme and a different operating system, and then or program. And then there is the HEP-fit more recently. And then there is the Z-fitter that was used in the old days for lab physics. So the outline of the talk is something like that. I want to give you some news on sine squared theta W, which is not directly a QCD parameter, but it is a fundamental parameter and very important. Then I go to these heavyweights. Then I talk about alpha S. So you see there are two determinations here. One is from lab itself, from the Electroweak fit, which it hasn't been discussed here yet. And the other one is tau decays, which have been discussed, but I find it important to have at least a second determination of alpha S and a different scale, because in the end we want to discuss or find perhaps deviations from the standard model. That's where we are, right? We don't want to confirm the standard model, we want to find deviations. And therefore it's important to have two different scales, because there could be new physics that in particular affects the Z-pole value. The tau value is probably not that much affected by new physics, but the Z-pole value might be, and if they're differing, then maybe that is a different way of searching for new physics. I do not know yet how much time I have for these other quantities, and then I want to have a brief outlook. So sine squared theta W, this is a summary of all the measurements of sine squared theta W with a precision of, I think, at least 0.5%. That was the cutoff. And what you see is quite a scatter in the different determinations. The upper part here is from the Z-pole, and then here now we have Tevatron and LHC. And now low energy experiments also start to measure sine squared theta precisely, and that will improve further in the future. So there's quite some scatter, but the average is very compatible with the standard model. The news is the most precise measurement of the weak mixing angle at lab came from the forward-backward asymmetry into B quarks. But for that, you need to know in order, well, at least in order alpha s squared, the correction to the thrust axis to know what is forward and what is backward. That hasn't been calculated until recently with a finite bottom quark mass, that two-loop effect. Now it has, and it actually had quite an effect. It shifted the forward-backward asymmetry, which was always deviating a bit, at least about a quarter sigma closer to the standard model. And the other thing that happened this year is atomic parity violation used to deviate from the standard model. Now it's pretty much in agreement because there hasn't been a new determination of what is called the weak charge of cesium. That is also an older experiment, like 20 years ago. But you need to know and understand well the atomic physics that goes into it. And one of the inputs is the transition vector polarizability that has now been measured very precisely and replaced, I think, a previously calculated value and has produced this shift in the extracted weak mixing angle from atomic parity violation. So coming to the colliders, if the average of LEP and SLC is shown there. Now the Tevatron and the LHC have compatible errors if one combines the different determinations at these colliders. And if one averages all of them, then one gets this number here, while from a global fit, you get this number here, and you see it's again in great agreement. So the sine squared theta W is looking good, even though there is this spread. So this is a very recent experiment. It's in parity violating electron scattering at very low energies. So using a beam energy of a little more than 1 GeV, one measures the difference in cross-section of left-handed versus right-handed polarized electrons on protons. Since the Q squared is very low, that means you can compute the process fairly reliably basically in an expansion of Q squared over the proton mass squared. The asymmetry is extremely small, 2.3 times 10 to the minus 7, and that asymmetry had been measured with only a 4% error. And so what one talks about the weak charge of the proton, which is some analog to the electric charge for Z bosons, and one measures the weak mixing angle like this. So this is a first measurement. It's in agreement with the standard model. And in the end, I will tell you how one can go from there and improve that further. So I'm coming to the heavyweights. This is the W boson mass measurements. And so there are fewer. And here, the situation is somewhat reversed relative to the weak mixing angle. Because here, if you see the most precise measurements of the W boson mass are actually in good agreement with each other, but there is some discrepancy opening up with the standard model. So for example, if I average the values of the W mass from the Tevatron and from the LHC by assuming that the smallest PDF error of all these analyses is common to both colliders, then that gives me this 7 MeV error from the PDFs that is common in the combination, and then I find an average of 80.379 plus or minus 12 MeV for the world average of the W mass. And now I do my global fit without the W mass as an input and see what I get if I use all the other information. And you can see it's a much lower value, and it deviates now by 2 sigma from the standard model. I am including, and I will come back to that, MT pole measurement from cross sections here, which I haven't done before because they used to be fairly large, especially if you take the pole mass from total cross section. It's still pretty large, like on the 2 GeV level, which cannot compete with a Monte Carlo mass that was discussed this week. But the differential distributions are more precise, and they become now relevant in the global fit. And these are first results that I'm actually presenting to you here, and they're preliminary. but I want to give you a taste what's happening. So these are the Monte Carlo mass measurements. They are in pretty good agreement with each other, except for the Chavitron, which finds a larger value. I averaged those by, again, assuming that the theory error, like Monte Carlo errors, PDF errors, etc., from the experiment that has the smallest of those will be common to all of them. And then I get an average, which is shown here, which is only 300 MeV in the determination, which is really outstanding. The main reason why the Tevatron differs from the other one is the lepton plus jet channel, which is always the most precise in all of these collaborations. And you can see there is a 2.8 sigma discrepancy between D0 and CMS at RAM2, for example. So from there, of course, the Monte Carlo mass doesn't enter electroweak precision physics. It's the pole mass, or more likely even the MS bar mass entering. So one has to make this step and somehow guess at what that would mean for the pole mass. I'm adding here what Benecke et al. Think is the renormalon error plus higher order terms in the relation between the pole and MS bar mass as an error. And then there is this correction where we have heard different talks about. I called it here delta Monte Carlo. That is an uncertainty, and maybe it is also a shift, and maybe it's universal, and maybe it's non-universal. I've learned here it's somehow believed now to be of the order alpha s times at some scale times that scale. If I now take that scale, for example, to be the top width, then I get a number of about 0.54 GeV, which one could then add, and for this talk I have added that as an additional uncertainty in this pole mass from the Monte Carlo mass. And then there are these pole mass measurement from differential distribution. There is the CMS result at run 2, just the TT bar for TT bar final states. This is the pole mass they get, but they also in the same analysis they get a value of alpha s, and that is correlated. They say it's only weakly correlated, but actually 0.3 is not such a weak correlation. But fortunately, they do give the correlation coefficient, so I can enter both of them into my fit. And then there is a second precise measurement of that type, which is from Atlas, TT bar plus 1 jet. So that's nice. It's a different observable. So I can assume that the theoretical errors are uncorrelated, and the experimental errors are certainly also uncorrelated because they're different detectors. And I can add this one as an additional constraint in my fit. They don't do the common fit with alpha s. They just assume from outside that that is the value. So I don't use that, of course, in the fit. So just to give you a flavor what happens, I can remove the Higgs mass measurement from the LHC, also from the fit, and then fit to it just from the precision data. And if I then also remove the top quark mass, then I get a result of the top mass, which is here, which has a fairly large error, but is consistent with what I was showing before. The Higgs mass has also a very large error, but is consistent with what has been measured at the LHC, and the goodness of the fit is very good. Now, let's add this Monte Carlo mass with an error from the conversion, as I said earlier, but no shift. Then, of course, the top mass will now be dominated by exactly that input, and the Higgs mass is going to be dragged down and its error reduced significantly, which is now not in agreement anymore with what has been measured by the LHC. And again, of course, why is that? It's basically the W mass. We have already seen that the W mass has a problem by comparing it with the standard model. And the goodness of fit, well, is still okay. Now you can repeat the exercise, no, sorry, here I put delta MC simply as to 0. So here I identified the Monte Carlo mass with a pole mass. Here I add an extra error. And here I also, just for illustration, I shifted the Monte Carlo mass, or the pole mass relative to the Monte Carlo mass by this 0.54 GeV. And you see that no matter what you do, the Higgs mass is always low and always deviating from the LHC value. And if you now add also this pole mass with this, remember this small value of alpha s correlated with the pole mass, then the Higgs mass gets dragged down even more. The top mass will go very low, and the goodness of fit, well, is still okay. And then one can again add these extra errors in the Monte Carlo mass, pole mass conversion, and one gets somewhat higher values of the Higgs mass. But you can see there is a 2 sigma problem always appearing. And if you use this pole mass value, the problem becomes a little bit worse. Now you can, of course, say 2 sigma I don't care about because there are many observables, especially in a fit like that. But there are only 2 that are really, really precise. And these are the first ones that I would expect new physics is affecting, the weak mixing angle and the W mass. Because these are like sub-per-mil precision measurements, and nothing can compete with that. And any kind of new physics you write down is, well, maybe not from the flavor sector, but any physics that affects sort of the hierarchy problem and so on is almost guaranteed to affect the W mass and the weak mixing angle at some level. So that's why I think it's interesting, even though it's only 2 sigma.
What is the chi-square if you put the value of the mass of the Higgs from the LHC?
Yeah, I have a global fit. I think it's 52 for 43. So it really gets worse then, of course, because then you shift it all into the chi-squared. Then everything looks good, but you shift it into a bad value of the chi-squared. Yeah. So this is what I just said graphically. You have the Higgs mass and the top mass. There are different sets of observables. The most important ones are, besides the direct measurements, the sine squared theta W and the W mass. And you can see the W mass is again lower than what has been measured over here. And now I can do yet another thing, is I can add the Higgs mass and the W mass and leave the top mass free and see what the fit gives. And it's higher than anything that you've seen. And it's again this 2 sigma kind of deviation. Alpha S. So alpha S from the Z-pole, that is the process we haven't discussed here this week. It is just as tau decays known up to order alpha S to the 4. There are some smaller but known corrections. There are further corrections of order alpha S squared and higher from singlet correction. Singlet in QCD only arises at order alpha S cubed. But here, because of the axial current, they already appear at alpha S squared. Moreover, they are proportional to MT squared or have a strong top quark mass dependence, so they're actually not that small. And if I just correct those coefficients to account for this kind of effects, you see that they change quite significantly. But that's basically how you get alpha S from the Z-pole in terms of the Z mass, the Z width over here. The error I just took as, I assume that the next order is just the ratio of these 2 coefficients. But then I assume that goes on forever. So I have to sum up this series because I have an error for all the orders. That's done over here. That gives a perturbative QCD error of a little bit less than 10 to the minus 4. And in terms of alpha S, it's still a small and in fact negligible uncertainty. There are other orders that are even more important, like alpha S. I think that is a typo here. That must be alpha S cubed, I believe, or order alpha squared alpha S. These kind of corrections also are known and introduce an error. But even with that, the theory error on delta alpha S on alpha S is relatively small. So in numbers, we have basically 5 observables at the z-pole that are particularly sensitive to alpha S, even though all the other observables also depend on alpha S, and that alpha S dependence is always fully taken into account. The z-width now gives us a value which is a bit larger than 0.12. And then there has been a shift for sigma hadron. What happened is there has been a reanalysis of the luminosity at lab by these people in this paper over here, and they concluded that the luminosity has to be the luminosity was higher than thought, which gives you an extracted value of the hadronic peak cross section by about 40 picobarns. And that, as you can see, changes sigma hadron by about 1 sigma. And sigma hadron is very important in the context of extracting alpha S. And it has shifted significantly up. It was always deviating by quite a bit. Now it's not deviating anymore and gives a value of alpha S that is in much better agreement with other determinations compared to before. On the other hand, there are these ratios of lepton decays divided by hadron decays, or in fact the other way around. And you can see here that the alpha S determinations of our E and our mu are actually in disagreement with everything else, and they are giving very high values of alpha S, except for our tau that is in agreement. And it is now that before that this was sort of canceling out the low value from sigma hadron and the larger value of those. That is not canceling out anymore, and the combination now gives a relatively large value of alpha S from the z-pole and has changed significantly from before. Then I also added the Higgs mass over here. That doesn't change the result very much. And if I also add tau decays, which I which I will discuss in the next slide, I get an average of these weak kind of decays, z decays and tau decays, and anything else that enters the global fit of a value given about here. So what do I do now with alpha S from tau decays? We have heard that it's on the one hand, it's a clean observable, but in the theoretical interpretation is difficult because of the low scale of the tau. So I take, as a master formula, I take the lifetime of the tau, and I also include the branching ratios of taus into electrons and muons and convert it into an additional measurement of the tau lifetime. The result is given here. And then I need an expression for, the gamma E over here and the gamma mu are clean. The branching ratio into strange can be taken from experiment or from the PDG. And then I'm left with gamma UD tau, which then is equivalent of measuring or calculating the tau lifetime. You have seen these kind of expressions before. There is this for loop, it's 5 loop, but it's alpha S to the 4 in the precision for the perturbative part. And then there is a non-perturbative piece that I come back to, and then there are some smaller corrections. Bottom and strange mass and charm mass effects are not included in here, but in the slide, but in the analysis they're relatively small. And this delta NP then is supposed to be a proxy for all the non-perturbative effects, including duality violations and higher orders in the operator expansion. There are basically 4 analyses, 2 from the organizer, one of the organizers here, using 2 different data sets from Opal and Aleph, and they don't seem to agree very well. Then there is this analysis by Davier et al. That also differs even in sign from this Aleph result based on the same data with an incredibly small error. I think that is almost certainly underestimated given all these spreads over here. And then there is another value over here that was given to me in a private communication. So then I just have to sort of average these things to this value over here. The central value, because of the different signs, is basically close to 0. Then the big question is, what will this error be in the future from this non-perturbative piece? Now, if we're now, with all this information at hand, and taking as the perturbative uncertainty, the last term in this expansion over here, with 100% uncertainty, and not putting any further guess coefficient that might appear in the 5th order and the higher orders, then one finds an alpha S for 3 flavors given over here with this perturbative error, which is now large enough to, in fact, also account for the difference between fixed order perturbation theory and contour-improved perturbation theory that we have heard about a few days ago. And this error over here is everything else, but it is dominated by this non-perturbative error here. And then I also give you values for the 4 flavor alpha S at m tau and the 5 flavor alpha S at mz, which is in pretty good agreement with lattice results and other determinations. So this is the error, again, from perturbative QCD. This is from everything else, and this is the total result. And if I add this as a constraint to the global electroweak fit, then this is the result from Z and tau. So to express what has happened with the luminosity in a slightly different way is the number of neutrinos, which is certainly not a QCD parameter, but it was sort of the pride of lab, that they determined that the number of active neutrinos is 3. Now, it was never really 3. It was 2.984, so it's 2 sigma away from 3, which was, in fact, this hadronic P cross-section. That was the main reason. In fact, this value is only from the hadronic P cross-section. That is what you see from the lab electroweak working group. In a global fit, you have somewhat more information, so you get a slightly higher value. That was in 2006, but it used contour-improved perturbation theory for the tau back then. Later, I decided to use fixed order perturbation theory, and that actually changed because sigma hadron knows about alpha S. It also changed the conclusion about the number of neutrinos from lab. So it's a little bit higher. The Higgs discovery now as a new input didn't change too much. But now, with the reassessment of the luminosity, you can see that this moved up by 1 sigma. So did this, and this is now in very good agreement with the number 3. And if I now take this pole mass from the cross-sections that I mentioned earlier, it's even closer to 3. This is the result of the global fit. I don't expect you to read these numbers, just the chi-square, as I said earlier, it's 52 for 44. It's not as good anymore, but it's hard to conclude anything from just this number. So I think I'm going to skip this part about other quantities of alpha and sine squared theta w at low energies, and rather, so this is the running of sine squared theta that you need if you want to interpret some of these low energy measurements that will be interpreted in terms of the weak mixing angle. And rather, I want to just come to a little bit of an outlook. So I mentioned this first result by the QV collaboration in polarized electron-proton scattering. There is now a new effort ongoing at Mainz. A new accelerator is being built primarily for this. It will be used for other things as well, but this will be the flagship measurement. They're going to use a much lower beam energy of 155 MeV, and the reason is at the one loop level, to interpret the weak charge of the proton, the gamma Z box enters. And the gamma Z box is a bit mean because the gamma is massless, so it checks all the scales, including the hadronic scales. So even though the weak charge is very clean at tree level, due to the gamma Z box, it's not so clean anymore. at the one loop level, and to make things worse, it depends on the energy of the beam. So the major uncertainty is proportional to the beam energy, and that's why they think they should make an experiment with a much lower beam energy, where this problem should basically be solved. The price to pay is that the asymmetry is even smaller, 4 times 10 to the minus 8. So you have two cross-sections that you compare at the level of 4 times 10 to the minus 8, and that with the precision of 1.4%. They think they can do it, and you can see here they would then measure the weak mixing angle with an uncertainty that by chance is exactly the one that we now have from the Tevatron and the LHC. They can also, if they add a few more hours, well, a few more thousand hours of measuring times, they can also measure the backward angle, and that is important to have an additional constraint on the form factors that enter at higher orders. Okay, so in my remaining 0 minutes, I just want to tell you there is a similar progress going on in electron scattering, same thing. Same process, same target, higher beam energy though. And they also, there's a first measurement using the E- arm of the SLC that has been done a couple of, 20 years ago. No, what is it, 15 years ago, with this result. And they also think they can push down the error on sine squared theta W to a precision that corresponds to the most precise value or the most precise measurement at lab. And it's a very clean process because it doesn't have any hadrons, neither in the initial nor in the final state. So that's my final slide. What can the FCC do if we have the full program that is now in a pre-CDR available and put all these estimated uncertainty from the FCCEE into a global fit, assuming that the theory errors can be brought down as well, which is a big assumption, of course, then the Higgs mass from the global fit just indirectly can be determined to 1.4 GeV. Now, if you would put the current central value from the global fit with that error and compare it with 125 GeV Higgs, you would have a gigantic discrepancy. So this is one way of looking forward to the future in this kind of precision physics. So this is my summary slide. I told you about some new developments from lab and atomic parity violation. There are these parity violating electron scattering experiments. Important results from the lab luminosity update. There is the top mass from TT bar production cross-section is no longer negligible, and there are interesting future developments. And with that, I finish.
Thanks for the talk. I have a question about how you combine the different LFS analysis from tau. So I understand that you try to get a representative value of the non-perturbative corrections.
Yes.
And then you do a careful treatment of R tau itself, and from that you get alpha S, right?
So I combined your two values just by weighted average. And then I added the one from Davier, not the one from Peak. I got a new average, and then I extended, I enlarged the uncertainty again so that it roughly corresponds to the value that you gave over here. So it's not too sophisticated, but
yes. No, but my question is, I mean, those non-perturbative contributions are correlated with alpha S in all the analysis, right?
Yes.
Because they're extracted together.
Yes,
so,
that is true.
What would happen? So I find this a bit, we never provided a correlation between this and our value of alpha S, although in principle this could be done. I would say we could compute that, but this is not computed. So this is a correlation that is not there, and it it's a correlation that would be in all the analysis, because all the analyses extract together alpha S and non-perturbative. So my question would be, if you just take alpha S from this analysis instead of doing this representative non-perturbative contribution, would this change the results?
Yeah, but I have to assume something. You mean if I put delta NP to 0, or?
Oh, you're putting the correlation between non-perturbative contributions and alpha S to 0 in your analysis.
Yes.
But this is not really true, right? I mean, these things are extracted together with alpha S, so they are correlated.
Then I ask you to provide me with a correlation.
Yeah, I know. I think we could do that perhaps.
Yes, that would be great.
But I'm asking, why this instead of just taking the alpha S values from the analysis? Because you could also just take alpha S directly and put them in your fit somehow, instead of taking the non-perturbative contribution and averaging.
Well, because first of all, my treatment of the perturbative part is also a little bit different from what you're doing, and it's updated in every call of the fit. So you have seen, for example, that the error is asymmetric. And the reason for that is if alpha S is larger, the alpha S to the 4 and all the missing terms will be larger compared to when alpha S would be smaller. That makes it asymmetric. So rather than putting an alpha S value and a constraint from tau, I recalculate even the error in every call of the fit. So it's a bit more complicated than just putting your result, for example.
So the global electroweak fit has a fairly small error bars now. So do you expect it will change the PDG average in the future?
You mean here? Or
yeah, well.
You're talking about alpha S or?
Alpha S, yeah.
This is because, if you put hold on, this is, you're comparing this with...
Okay, so you had alpha S before, which was 0.192. So that's a global electroweak fit, and then you have 0.173 on the next slide. So kind of...
So, I mean, I have to admit that this table is not updated. This is basically, no, it is updated. Hold on. You're right. Let me. This is 11. Oh, yeah. So this value here did not yet include the top mass from the cross section. And the cross-section, to be consistent, I have to put the alpha S, which is very small, and that drags it down.
Okay.
So, and as I said, it's preliminary. I do not know yet whether, for example, for next year's PDG, whether I really use the pole mass from the cross-section. Probably I should, but I have to decide, because as you can see now, it has quite a significant effect.
What kind of new physics can help to alleviate the tension with the Higgs mass? What kind of new physics can help to alleviate the tension with the Higgs mass?
Almost anything, because you need basically a contribution to the W mass. So the W mass, among other things, knows about the T parameter, which is basically the ratio of neutral current to charge current interaction strength. And even a Z prime, for example, would change dramatically the relation between the W mass, the Fermi constant, and the weak mixing angle. So even the simplest scenarios that you can imagine can easily shift the W mass and therefore the discrepancy with the Higgs. The problem is that then we should also by now see the new particles that makes those shifts in the loops. And we haven't seen them yet. So that is the caveat. But of course, it could be some stop that is hiding in the data and so on.
What is currently the inputs that gives you the most pull on this global electroweak fit?
That would be the W mass, and still the forward-backward asymmetry into B quarks, because you saw it's still deviating. The left-right asymmetry from the SLC, which is deviating in the opposite direction. And of course, G-2 that I didn't talk about. And it is correlated to some of the things over here because it's the same vacuum polarization contribution that enters the running of alpha that is very important at the Z peak, and as you know, G-2. So there are, and the running of sine square theta as well. So there are all these crosstalks that also involve the charm mass, by the way. So here, then he closes the loop to this workshop, because the charm mass is necessary if you compute these things in perturbation theory. And that's what I'm actually doing for the heavy quark contributions.
So I have a perhaps naive question. You talked about how the top Monte Carlo mass coming from the tevatron is in tension with the measurements of this quantity at the LHC. My naive understanding perhaps is that this Monte Carlo mass is somewhat of an effective quantity, and the energy at the tevatron is so much smaller. I mean, the jets look very different, right? The TT bar production at the tevatron, the TT bar pairs aren't boosted very much. Is this really something that people think they have so much theoretical control over this quantity that they should agree at the level of the errors, or is this just...
Well, there are experts here, right? But this is basically this word non-universal question mark. So yes, it is absolutely conceivable that it is square root S dependent, among other things. And it could be that, of course, that this delta MC is different for the tevatron relative to the LHC. And it could be non-universal in other respects, of course. But I think there are other experts here that can say that in a much better way.
I can say something. These analyses are based on a Monte Carlo that uses a Parton shower. And the Parton shower is only accurate if tops are boosted. You can argue that they are boosted at the LHC, but the tevatron, as I say, that are very slow tops. So maybe the whole Monte Carlo setup is just not even working.
So that would mean that the tevatron error is way underestimated, you're saying, or?
It means that you have a problem already with your Monte Carlo. Right?
Yeah, but...
So you can blame it in the Monte Carlo, probably, yes.
Okay, are there?
Yeah, maybe just a follow-up comment. So I don't know if they're using the same Monte Carlo for tevatron analysis as they do for LHC. Have they updated the Monte Carlos when they put this 2016 paper out? Or was it the old Monte Carlo at the time of the tevatron?
I think in their own average, they went to, well, they went to common PDFs, maybe not to a common Monte Carlo. So they tried to be as similar as they could at that level.
Because the Parton shower differences can also factor into this discrepancy.
Now, of course, I mean, I would then argue if this delta MC, whatever it is very different for the different colliders, it would be actually good news, because then it would be uncorrelated. Here I'm assuming pessimistically that it's completely correlated, and therefore the whole error would be increased. If they're uncorrelated, the discrepancy would be larger, but the combined error would be smaller.
Also, the Monte Carlos, they keep getting improved. And, okay, I'm not going to go further because I was going to mention unfolding, but there is no unfolding in these measurements. Yeah, they're just using direct Monte Carlo and detector level data.
Yes, I think
yeah,
so.
okay.
Are there further questions or comments? If not, let's thank Jens again and all speakers. And as the chair of the last session, it is my pleasure to also for all of us, thank our very kind hosts and the organizers for putting together such a beautiful workshop. It was really, for me, it was a very nice environment, lots of very interesting discussions.